The ultimate goal of modern spatial computing is to successfully convert flat, two-dimensional data arrays into fully navigable, three-dimensional structures. Standard pipelines typically rely on iterative refinement, calculating a rough estimate, measuring error, and repeating the process to gradually improve depth. HiWorld 2.0 uses a different approach, moving directly from input to output without a feedback loop. As shown in this flowchart, the sequence is a single forward pass. There is no second step. The model calculates the geometry in one movement and does not return to the initial data to correct its estimations. This architecture addresses the computational cost of spatial reconstruction by removing the requirement for iterative refinement. Generating these structures requires raw input, such as standard photographic frames or continuous video. This visualization represents the three structures generated simultaneously from that input: a dense point cloud, a connected polygonal mesh, and a collection of volumetric Gaussian ellipses. These layers exist as distinct mathematical descriptions of the exact same physical volume. The system outputs objective coordinate data intended for machine parsing and spatial navigation. This final output serves as foundational architecture, a highly stable, standing geometry that can be accurately projected and viewed from absolutely any angle. The pipeline begins at Node 1, the entry point for visual data. When provided with continuous video, the system automatically parses the motion into discrete, individual frames. This diagram shows the spatial density rule in action. As the camera moves, the system extracts high concentrations of frames specifically where perspective shifts occur. When the camera is static, frame extraction becomes sparse. Processing redundant angles offers no new spatial information and increases memory load without improving the mesh. However, visual input alone lacks a mathematical ground. The system cannot orient these images in space without secondary anchors. This intelligent pruning at the point of ingestion is the first step in managing memory usage throughout the pipeline. To orient the data, the system requires Node 2, the camera prior. This prior acts as a mathematical anchor, locking the extracted two-dimensional frames into known three-dimensional coordinates. This 4x4 matrix grid defines the spatial ground truth. Without this anchor, the model may generate misaligned geometry or hallucinate spatial relationships. Node 3 adds the depth prior. Here, horizontal depth gradients are paired with the fixed camera positions to define absolute volumetric distance. Every two-dimensional image must map securely to a corresponding depth constraint. The architecture is rigid regarding file syntax and naming conventions. If a photo is labeled with a lowercase extension while the depth array expects a capital letter, the mapping fails. The system does not flag the error, it simply terminates the prior. This silent failure removes the mathematical constraint, which can degrade the final geometry without halting the pipeline. Absolute precision in the data structure is the requirement for maintaining speed in a single-pass system. Once grounded, the pipeline must operate within the physical constraints of the hardware. The target size variable forces the longest edge of input images to specific mathematical multiples of 14. As this graph shows, geometric detail rises linearly alongside the image resolution. However, the VRAM cost is not linear. It curves upward in a sharp parabolic path. GPU memory load scales quadratically against image resolution. When the resolution increases past a certain point, the memory load crosses the hardware threshold and causes a failure. Standard hardware cannot overcome a quadratic curve through processing power alone. Managing these costs requires granular control over the memory budget. To manage the quadratic memory trap, practitioners use the system's built-in filtering tools. The mask stack filters raw geometric outputs before they are stored in final memory. This stack removes low-confidence outliers, edge fuzz, and background data, isolating the necessary structural points. This diagram shows the output manifold, which splits the data into 5 distinct channels. The tracking bar on the right measures the total VRAM usage. Disabling unused output heads, such as normals or point clouds, immediately reduces the VRAM load. Efficiency in this pipeline is achieved through the strategic refusal of unnecessary data. At the point of execution, all inputs, priors, and constraints converge. The input path and the mathematical priors route into a single processor block simultaneously. This represents a high-density computational load of multidimensional matrices. The execution occurs in one consolidated movement. All 5 output channels emerge from the block at the same instant. There is no sequencing or feedback loop required to resolve the data. The architecture resolves immense spatial complexity without relying on sequential processing steps. The result is a stable, objective geometric state. This output is distinct from conventional generative video, which relies on a sequence of frames. As shown here, the final products are self-contained data structures routing to distinct ports. This geometry can be queried from any coordinate and dropped directly into external technical pipelines. The system provides a functional foundation for spatial computing by delivering objective structural data.